Hello everyone and welcome to the Pre-Calculus/Trigonometry Week 8. This is going to be the last lesson. We're going to be talking about the trig identities, one of the most complicated of all the lessons. I'm not going to lie, today's going to feel like I'm throwing a mountain of information at you to memorize, and it won't come into play until like the end of the year. So basically, after today, I'm going to give you the homework. I encourage you to do the homework, and then after that, we're done, and I'll probably send you a write a review sheet to ask you what you thought of the online course this summer, because I value your feedback. So without further ado, let's go ahead and get into the trig identities, which is what today's going to be all about. So if you remember, last week we were talking a lot about the different sine, cosine, tangent functions. In weeks past, we talked about graphing the sine and cosine graphs specifically. Today we're going to be looking at the different properties, or we call them identities, of these trig functions, sine, cosine, tangent. And specifically, we're going to be looking at what they call the trig identities. And then after we learn the trig identities, we're going to be looking at one of the most famous examples in all of pre-calculus, and that's trig verifications. And again, you're going to see that towards the end of next year. So I promise you will see it. And let's talk about it. First, we have the reciprocal identities. Basically, you have no idea what CSCR or SCS is or COT. So let me tell you. CSC simply stands for cosecant. It stands for cosecant. C-O-S-E-C-A-N-T. Cosecant. SEC stands for secant. The reason why it's called cosecant, by the way, is because it's the complement to secant. That's why it has co in front of it. By the way, that's why it's called cosine, because cosine is the complement to sine. And then cotangent, cot is really cotangent, the complementary trig function to tangent. So that's what these words stand for. And basically what this means is that if you have 1 over sine, it's cosecant. If you have 1 over cosine, it's secant. And if you have 1 over tangent, it's cotangent. And I'm going to be expecting you to know these words as we go throughout today. And I know it's going to be hard because you just learned this. But I'm still going to be putting pressure on you to memorize it, so get ready for that. Next, we want to talk about the cofunction identities. Cofunction identities, not that bad. Basically, what we say is if you have pi over 2 minus theta, specifically pi over 2 minus theta, which if you forget, pi over 2 is 90 degrees if you prefer degrees, but I'm going to be saying pi over 2 today. If you have pi over 2 minus theta, for any of the trig functions, it's going to give you its complement. What do I mean at the complement? Well, the complement to sine is cosine, so these two are a family together. The complement to cosecant is secant, so they're a family together. And then the last grouping would be tangent and cotangent. So if you see pi over 2 minus theta, or x, because it's just a variable after all, then you're going to get any one of the three families here. You're going to get its complement. So hopefully that makes sense. And by the way, there's a proof for this. I don't think I want to prove it today because I think it's a little too advanced. But just know that this has a lot to do with transformations, which we talked about in week 3. And if you do the right transformation with the shift and the x-axis reflection or the y-axis reflection, then you will get the same graph as before. So that would take a while to really understand that. So just memorize these. It'll save you the trouble. Next is the Pythagorean identities. These are 3 very famous, probably the most famous identities, especially this first one. Sine squared plus cosine squared equals 1 is one of the most famous identities in all of pre-calculus. Again, it doesn't come until like the end of the year, but once you see it the first time, you're going to see it like 5 to 10 more times each week when you're in pre-calc. And then you're going to just have to memorize these 3. So the 3 are sine squared plus cosine squared equals 1. Notice all 3 of these have squared in it. You need squared in order for these identities to work. The next one is tangent squared theta plus 1 is secant squared theta. And then the last one is cotangent squared theta plus 1 equals cosecant squared theta. So basically you notice that like the second one and the third one are basically the same thing, except you just replace, tangent with cotangent and secant with cosecant, and that makes sense. And then the only one that's really different is the sine and the cosine one. And then the very last thing I want to talk about is even and the odd identities. If you remember way back, I think it was week 4, when we talked about even and odd functions, we said that even functions are functions, even functions are where f of x equals f of negative x. Not sure if you remember that, but that's what we said. cosine and secant are even. Cosine and secant are even. Which makes sense because secant is really just 1 over cosine anyway. But cosine and secant are both even. It's because if they have a negative theta there, it's still going to be positive anyway. And then sine, tangent, the rest of them, all 4 of those are going to be odd functions. And remember what odd functions are. Odd functions say, if you have f of negative x, it's going to be negative f of x. In other words, the negative sign in the middle can be put out in front, if you want to think of it like that. So these 4 are odd functions, and I will be referencing that later today. I'm going to give you a second to write it down. But are there any questions on anything I just said from this first page? Okay. Now, before we apply these identities, I just want to make sure we know them. So in other words, next page, let's practice. And I'm going to be asking for audience participation. So if you're watching at home and you're watching the recording, just pause the video, see if you can think of it. If you can fill out this page without looking back at your notes. But I guess I really don't need audience participation, but I guess I'll ask anyway. Who knows what cosecant theta will be in terms of the identity? The answer is 1 over sine theta. Secant theta, that's 1 over cosine theta. And cotangent theta is 1 over tangent theta. Remember, these are the reciprocal identities. The next 6 are the cofunction identities. Remember, sine of this becomes cosine of just theta. All the pi over 2 and the minus stuff, that just goes away. So it just becomes normal cosine. Next, cosine becomes sine theta, because remember, they're complements of each other. Tangent will become cotangent of theta. Skipping to the bottom right, cotangent will become tangent of theta, because again, they're complements. And then finally, secant and cosecant are complements of each other. So it's cosecant of theta, and then last, secant theta. And that's what we're going to put for the cofunction identities. Again, I hope you're trying these on your own before you just look at the answer. And then next is the 3 Pythagorean identities. Remember, sine squared plus cosine squared is 1. Tangent squared theta plus 1 is secant squared theta. And then cotangent squared theta plus 1, that's going to give us cosecant squared theta. And then the last 6 here, these are the even and odd functions. So remember, sine and tangent and cosecant and cotangent are odd functions, meaning that when I see sine negative theta, I just put that negative sign out in front, so it's negative sine theta. Same's going to go for tangent theta, because that's going to be negative tangent theta. I know I'm jumping around, but I'm just getting the odd functions first. Cotangent negative theta is going to be negative cotangent theta. Cosecant, same thing, it's going to be negative cosecant theta, because that is all the odd functions. And then the 2 even functions, cosine and secant, they just become normal cosine and normal secant. There's no negative signs at all for cosine and for secant. So there we go. We just filled out basically all the identities over again as a good practice. Any questions on any of that? Okay, next, I'm going to be asking you, write each Pythagorean identity in 2 new ways. I'm going to be doing the first one I'm going to probably do all 3 for us. But I especially want to do the first one for us because I want you to think about it. Basically, if I have sine squared theta plus cosine squared theta equals 1, and I want to write this a new way, I can subtract cosine squared theta from both sides, and that will give me sine squared theta equals 1 minus cosine squared theta. And that's a new way. You just created your own new Pythagorean identity. Look at that. And then I asked myself, well, what else could I do with this function? Well, couldn't I also have subtracted sine squared theta from both sides? And the answer is yes, of course. And if I subtract if I subtract sine squared theta from both sides, then I'll get 1 minus sine squared theta. And we will be using both of these later today in the trig identities, or verification problems, I mean. So that's it for the first one. Now, using the same logic, you can probably come up with the next 2, but just in case you can't, I'm going to help you. For this one, I can subtract 1 from both sides. So that means tangent squared theta equals secant squared theta minus 1. So there's one of my trig identities. And then the other one I can get if I just subtract the other one. If I subtract tangent squared theta from both sides. And in that case, I'll get 1 equals secant squared theta minus tangent squared theta. And there's the second one. Any questions on any of those? Okay, great. And then one more. Again, I encourage you to try it on your own. But cotangent squared theta plus 1 equals cosecant squared theta. Again, I can subtract 1. Cotangent squared theta equals cosecant squared theta minus 1. That's one of them. And then the other one you just get if you subtract cotangent squared theta instead. So in other words, 1 equals cosecant squared theta minus cotangent squared theta. And so the next time your mom asks, or your dad, or whoever, asks you how many pancakes do you want? Instead of saying you want 1 pancake, you can say, I want cosecant squared theta minus cotangent squared theta. And even though they'll have no idea what you're talking about, by law, they still have to give you 1 pancake, because that's 1. Or at least math law, not like real laws. Any questions on any of those? Okay, great. Next, before we get into trig verifications, which I keep alluding to them, they're coming, don't worry, I just want to do some practice with simplifying trig expressions. Because basically, all trig verifications is simplifying these trig expressions using the reciprocal property, the cofunction identity, the Pythagorean identity, all the identities we talked about before, plus splitting things into sine and cosine. So if I could give you one tip for all of these that you see in front of you, split into sine and cosine. That's the best advice I can give you. So basically, if something is not sine or cosine, I'm going to rewrite it. For instance, I look at 1 over cosecant x. Hey, that's the reciprocal identity. I know 1 over cosecant is equal to just sine x in the numerator. Because it's, you flip it, you take the reciprocal. So that first one's sine x, super easy. Next one's a little bit harder. Sine x times secant x. Well, sine x stays the same because it's already sine. And then secant, I'm going to rewrite as 1 over cosine x. Because again, I want to rewrite my everything into sine and cosine. So notice, when I multiply these together, I get sine x in the numerator and cosine x in the denominator. That's just simple multiplying fractions. And then sine over cosine, hopefully you remember this, this is just tangent. Tangent is sine over cosine. I'm not even sure if I ever explained that well, but I'm telling you now. Tangent is sine over cosine, therefore this all simplifies. Sine x secant x that we started with simplifies to just tangent x. And then the very last one, yeah, there's going to be a lot of stuff here. But first tangent splits up into sine x over cosine x times cosine x. I'll write cosine x over 1 to remind myself this is fractions. And then cotangent x is, you can say 1 over tangent x, that's fine. But if it's just the reciprocal, then I think it should be cosine x over sine x because it's the reciprocal of tangent. And earlier we just said tangent was sine over cosine. So then multiplying these, I would say a sine cancels there, and then a cosine cancels there and there, or you could choose the middle one technically. Either way, you're left with just a cosine x, and that's all that is. Pretty cool. Any questions on any of those? Okay then, with that we move on to trig verifications. Just to show you what an example looks like, here's a statement. Prove that sine x times secant x equals tangent x. Actually, we just did that on the last page, didn't we? Sine x times secant x, we ended up getting tangent x. Now, here's the thing about the problems we just did a minute ago. It said simplify the trig expressions. How do you know when to stop, right? Because technically you could have stopped here, sine x over cosine x. And I would, if I was your teacher, I would say that's right. You don't have to write tangent x. How do you know when to stop? Well, in the simplify ones, you just simplify as much as you can, as much as you're able to. In a trig verification, x marks the spot, no pun intended. You got to go to what it says you need to equal it to. So sine x secant x equals tangent x. You start here, you got to make it look like tangent x. Simple as that. And the other thing I want to tell you is that technically you can change both sides. So for instance, if you think it'd be easier to go the other way, tangent x to sine x times secant x, you can go in reverse as well. The problem is it's going to be kind of impossible because there would be a lot more freestyling, if you know what I mean. So here's some strategies to help you with trig verifications. First strategy, always start with the side that looks harder. I want you to start with the side that looks harder to solve, which is ironic. But look at this. Sine x times secant x. That looks harder than tangent x, right? Start with that side. It's actually going to be easier, as it turns out. It's the opposite of what you'd expect. Strategy number 2, break up everything into sine and cosine. We mentioned that on the last page. And the reason why we do that is because once you're in sine and cosine, that's like your building blocks. Like, you know how all the elements, and if you've taken chemistry before, you know how you have compounds like hydrofluoric acid or any kind of compound. All the compounds remain to elements, basically. Well, sine and cosine are your elements, and you can make a ton of compounds with your elements. And then finally, step 3, the third strategy is use the trig identities that we just learned on the first page. And so, for the rest of today, and even on your homework, if you need to flip back to that sheet, I will gladly let you use your trig identities so you don't have to memorize them. But I will say this, that even if I give you the whole sheet, it's not going to give you the answer just there. There's still a lot of work on your own part that you have to do. So for the next problems, we're going to be, and honestly for the rest of today, we're going to be verifying the trig identities. So for instance, with this first one, again, it's one we already did, sine x secant x equals tangent x. First thing I would do, sine x times secant is 1 over cosine x. I would then write that as sine x over cosine x, and then I would say sine x over cosine x is the same thing as tangent x. And then what do you write when you're done? Well, what I like to do is I like to write tangent x equals tangent x and then a little check mark to prove that, yes, I got the same thing. This is probably the only time ever in math where you don't have to circle your final answer. I suppose you can if you want, but all of your answer is the work along the way, all of it. So for instance, if you really get stuck here, and for instance in the next one you give up and you just say, oh, this negative sine squared x equals negative sine squared x, I would say, yeah, sure, you got it, but like you clearly didn't understand anything what you just did. So I'd give you 0 points for that. In other words, what I'm trying to say is don't skip any steps. If you do, you're going to lose points, I promise. Okay, number 4. Cosine squared x minus 1 equals negative sine squared x. And we have to prove that these two are equal to each other. First, I want to start with the harder side to solve. I would say this side looks more complicated, so start with that one. And then I ask myself, well, break it up into sine and cosine, which it already is. Like everything here is in sine and cosine already, so I don't have to do anything. So then the last thing I'm going to do is I'm going to say, hey, what are my trig identities? And to me, this looks very similar to the Pythagorean identity, specifically the one we wrote on this page right here. Right, where was it? Right here. Remember we said sine squared theta equals 1 minus cosine squared theta, and we said cosine squared theta equals 1 minus sine squared theta? Well, I'm going to fill that in right here. And I'm going to say cosine squared x is the same thing as 1 minus sine squared x. Everyone see what I did? I just replaced cosine squared x with 1 minus sine squared x because that's a Pythagorean identity. And then minus 1. And then the 1's cancel here because even though this is in parentheses, it doesn't really matter. So the 1's cancel. I just have negative sine squared x equals negative sine squared x. Check mark. We're done. And again, the reason why is because of the Pythagorean identity. That was an easy one. Most trig identities take way more than just 2 lines. Any questions on that one? Okay, next, number 5. Number 5 says we have 1 over 1 minus cosine x times 1 plus cosine x, and that must equal cosecant squared x. Okay, so how would I solve this? Well, first I start with the more complicated side, which is certainly the left. Break it up into sine and cosine, which it already is, and then I have to use my trig identities. Now there's a fourth strategy I didn't say, probably should have said it. If I were to add it to the list right here, strategy number 4, simplify. Simplify. It's always a good idea to simplify. That's always a good strategy. As a matter of fact, if you want to start with simplify, I'm okay with that. You can do simplify at any one of these steps. 1, 2, or 3. So here's what I'm going to say. If I want to simplify this, I can FOIL the denominator. The numerator is still 1, but the denominator is 1 times 1 is 1. Negative cosine x times 1 is minus cosine x. 1 times positive cosine x is plus cosine x. And then negative cosine x times positive cosine x. That's confusing, but it is negative cosine squared x. Notice the cosines cancel like that. And now you're left with 1 over 1 minus cosine squared x. And hey, 1 minus cosine squared x, we know what that is. We just said it a minute ago. That's sine squared x. So it looks like I got 1 over sine squared x. And I forget, when do I know when I'm done? Oh yeah, I have to have it equal to cosecant squared x. So I'm right here right now. I need it to equal cosecant squared x. And I would say this is a reciprocal identity. So for that reason, cosecant squared x equals cosecant squared x. Check mark. Done. Again, that was the reciprocal identity. I believe when you look at the answer key to this week's homework, I'm pretty sure I give every reason why it works. Almost like a proof from geometry. I say reciprocal identity. I say break into sine and cosine. I say cofunction identity. You don't have to do that. At least my teacher didn't make me do that when I was in high school. Of course, I don't have the same high school teacher as you, so you very well might be forced to give the identity why. But in general, it's okay if you just go straight from here to there because it's clear that you did a reciprocal identity. Next is number 6. We have tangent theta plus cotangent theta equals secant theta times cosecant theta. Here it's not super obvious which side to start with. I would say the left side's harder because, addition and for the fact that you're going to be breaking up into sine and cosine. Just look at this. Tangent is sine theta over cosine theta plus cotangent theta is cosine theta over sine theta. And now if I wanted to add these two fractions together, you probably already know I need a common denominator. So this is going to be really hard. So first I'm going to multiply the left one by sine theta over sine theta. In other words, let me write it out. Sine theta over cosine theta times sine theta over sine theta, because that's what's missing from the denominator. And then plus, this one's missing cosine in the denominator, so I have to multiply it, cosine theta over sine theta. I need to multiply it by cosine theta over cosine theta. Okay? And then the numerator here, it's going to be sine squared theta. In the denominator, I have sine theta times cosine theta. And then plus cosine theta times cosine theta, that's cosine squared theta. And yes, you need to recognize that with the squared. Divided by sine theta over cosine theta. Because these two denominators are the same, I can now write them as one fraction. In other words, I've got sine squared theta plus cosine squared theta all in the numerator. And in the denominator, I have sine theta times cosine theta. Hopefully you recognize what the numerator looks like. Sine squared theta plus cosine squared theta, that's just 1, because that's a Pythagorean identity. And so for that reason, I've just got 1 over sine theta times cosine theta. But the question is, am I done? Well, remember, I wanted it to equal secant theta times cosecant theta. And I would say right now, this is not enough, there to just write they equal each other. I don't think this is super obvious. Can someone tell me why they're equal to each other? The secret is... Go ahead.
The reciprocal identity.
Because of the reciprocal identity?
Yeah, because 1 over sine theta plus 1 over, multiplied by 1 over cosine theta equals that.
You're exactly right. If you split apart the denominator, which you can do, by the way, if this was if this was addition in the denominator, you couldn't do this. But because it's multiplication, we can. And now, yes, we definitely have the reciprocal identities. I would just finish it off by writing secant theta cosecant theta equals secant theta cosecant theta. Check mark, done. And I remember when I was doing these in high school, these were some of my favorite problems to do in pre-calc because it almost becomes a little puzzle, a little brain teaser. The only time it's not fun is when you have no idea how to solve it and you're completely lost. Then it's not so much fun anymore. But when you're solving it, when you're getting the right answer, oh, it's a lot of fun. I love it. So that's it for that page. Next we have number 7. Number 7, we have sine x times cotangent x plus tangent x equals secant x. We're definitely starting with the left side. It's like 10 times harder. And I also want to tell you there's like two different things you can do here. Like for instance, the first thing you could do is distribute the sine to both of these things. You'd get, sine x times cotangent x plus sine x times tangent x. But I'm actually not going to do it that way because I prefer, instead of distributing first, I prefer to break everything in terms of sine and cosine. That's just me. You can do what you want, technically. There's more than one right way to do these problems. So what I'm saying is sine x times cotangent, like we said earlier, is cosine x over sine x plus sine x over cosine x. And then what would I do from here? Well, you can do one of two things. Number one, you can distribute the sine now if you wanted to. Again, I'm not going to do that. I think it'd be better to get a common denominator because that will get us to a single fraction. In other words, if I do distribute, the problem is I'm still going to have two fractions. I don't like that. I'm going to have to get a common denominator eventually. Might as well start now. And the truth is, this one is exactly the same thing as the last one. You can even look back at the last problem. This is exactly the same thing. It's going to be first the sine x out in front. Now, the first fraction becomes cosine squared x over sine x cosine x, and then plus sine squared x over sine x cosine x. And again, that's getting a common denominator by multiplying the left one by cosine over cosine, and then I multiply the right one by sine over sine. That's how I got this. It's not just magic, although it looks like magic sometimes. I'll tell you, if you want to know what magic looks like, take Physics 2, electricity and magnetism. If you ever have to take that class in college because you're like an engineering major or something along those lines, I do not envy you. I essentially took that class 3 times in college because I was an electrical engineering major, and believe me, it wasn't fun the first time, wasn't much better the next 2 times. But I got an A in the class, so can I really complain? Anyways, here, sine x times numerator, cosine squared plus sine squared. We already said it before, it's 1. So it's 1 over sine x times cosine x, and now I can multiply these together. To me, it looks like the sine will cancel in the denominator, and so I'm really just left with, I'll write in the space to the right here, all I'm left with is 1 over cosine x for the left side, and the right side is still secant x. And hopefully you realize here, this is just the reciprocal identity. So secant x equals secant x, check mark, we're done. Do you actually have to write check mark when you're in school? I don't know, but that's what I did, because that's what my teacher told me to do, and it makes sense to me. But of course, all the work leading up to it is the most important part. Any questions on that one? Okay. So I have a feeling it's going to be a short lesson today because we're already on the last 3 problems that we have together, and all 3 are going to involve the hardest case, which is the co-function identities and the even and odd identities. As a matter of fact, I don't know why I did this. Number 8's like the hardest one out of 8, 9, and 10, but that's okay. So anyways, with number 8, tangent of theta minus pi over 2 equals negative cotangent theta. Well, the first thing you could say is, oh, that's a co-function identity. This is just cotangent theta. And I would say, no, wrong. Why? Because look back at your co-function identities. If you look back at them, it has to be pi over 2 minus theta. That's not what we have. Shoot. The secret is, just like we would do back in transformation days, you're going to have to factor out the negative here. So really, it's tangent of negative pi over 2 minus theta, close parenthesis, close parenthesis. And that is what we're going to work with now. And the reason why this works so well, this is not the co-function identity yet. Because if you look at your co-function identities, you don't have a random negative sign out in front, right? So instead what I'm going to do is, I'm going to say, hey, this is an odd function. And because tangent's an odd function, that negative sign gets to move out in front. So really it's negative tangent of pi over 2 minus theta. And can you really move out that negative even if there's more to the equation in there? And the answer is yes, you can move that negative sign out in front like I just did. Now we have the co-function identity, so just the tangent part becomes cotangent theta, but because the negative sign carries over, negative cotangent theta equals negative cotangent theta, check mark. The secret is whenever you have a co-function identity that looks like it's in the wrong order, you just got to pull out the negative and do it again. You'll be doing that on the homework, so get ready. Any questions on number 8? Okay, now the last page that we'll ever have together, unless you meet with me for some other reason. So number 9, sine of negative theta divided by sine of pi over 2 minus theta equals negative tangent theta. One thing I do want to mention, every problem we've done today, including the last one I'm going to say, every problem we've done today, we've looked at the left side only, changing the left side. I don't think that's very good of me. In other words, I should have put a few examples where I did the opposite. I should have put the harder side on the right. I'll learn for next year. But what I want to tell you is that technically, you can change the right side. You can even change both sides if you want to. As a matter of fact, for the last problem, I'm probably going to change both sides. I'll just tell you that right now. But anyways, for this problem, definitely start with the left. The numerator is an odd function identity. So in other words, the numerator is actually negative sine theta, because sine is an odd function, so the negative sign goes out in front. And then in the denominator, we just have a normal cofunction identity here, because it's pi over 2 minus theta. So in other words, that's just cosine theta. And then negative sine over cosine, is that good enough? Well, we need to get to tangent. And of course, I know sine over cosine's tangent. So negative tangent theta equals negative tangent theta, and then we're done. Any questions on number 9? Okay then, the last problem, number 10. Cosecant of pi over 2 minus theta times secant of negative theta equals tangent squared theta plus 1. Here's what I say. First, I clearly have the cofunction identity here, and I clearly have the odd/even identity here, but secant is an even function. So that means that negative sign is just going to go away. So first cosecant becomes secant, so it's secant of theta, times, like I just said, that negative sign goes away, so it's just another secant theta. Makes sense so far? I got 2 secant thetas here. Because I'm multiplying them, this is just going to become secant squared theta. And remember, I got to have secant squared theta equal tangent squared theta plus 1. Some of you might not see this, others of you do. But hopefully you realize this is one of our Pythagorean identities. And as a matter of fact, for once, I'm going to change the right side. And I'm going to say that tangent squared theta plus 1 is secant squared theta. If you don't believe me, look back at the first page. Secant squared theta equals secant squared theta. Check mark. We're done. If you wanted to do this instead, if you wanted to change secant squared theta into tangent squared theta plus 1, in other words, the last thing you'd have is tangent squared theta plus 1 equals tangent squared theta plus 1, and then a check mark. You can do that as well. They're both right. Because what's important is not the final answer, it's the process, the steps leading to it as the final answer. So is there any questions on that one? Okay, so then in that case, I want to leave you with this. Basically, what's my story? What's the story of Dan the Tutor? And I just want to remind you, why was I doing this for free 8 weeks in the summer in the first place? Number 1, I did it for 8 weeks and not longer because I'm going on a trip to France next week with my fiance. Very exciting. Even more important than that, why am I doing it for free? I'm doing it for free because I'm hoping that all of you watching the video or attending the live lessons will tell your friends, will tell your teachers, will tell whoever, parents will tell other parents, post on social media, whatever. Eventually down the road, this will pay off, okay? Maybe even you see me for tutoring down the road. I hope so. I hope to see all of you. I know I won't, but my dreams can be my dreams. But I know for a fact that the reason why I'm doing this is because I don't want to just tutor you for the hope of getting monetary profit in the future, although that's one reason. The bigger reason is because I don't just want to make money tutoring. I want to become the greatest tutor of all time. And that goal means sometimes you have to work for free. It means that sometimes you have to give value even when you're not expecting anything in return. And at the end of the day, when you're tutoring and you're starting a business and no one knows who you are and you're starting from scratch, sometimes you have to start from free. And literally back in 2020 when I started my business during the pandemic in the summer, literally I was tutoring for free. And by the time the fall came around, I had my first paying customer. And by the time that the spring came around, and, everyone, I met with probably 30 different kids between those 2 semesters that first year. And believe me, I made a lot of money. But literally, none of that would have started if I wasn't willing to put in the work for free at the very beginning. So I'm not saying you always have to work for free. But what I am saying is, if you love what you do, then working for free, it doesn't even feel like work. So with that message, I hope you have a great rest of your summer, and I hope you have a great rest of your high school or college. Maybe you're not even looking at colleges yet. Whatever. I hope that wherever your future lies, I hope you have a great future and one where you love what you're doing and make a positive impact on the world. So thank you all for joining me, and hopefully I'll see you later. Bye-bye.